Yeah, thank you for the introduction. And also, I would like to warmly thank the organizers, especially Michal and Johanna for the invitation, for setting up all the details about my trip. And finally, because I could not come, unfortunately, for arranging this video. So this work is the result of a collaboration between myself, so in Dijon, in Burgundy, and the group of Olivier Dulieu in Orsay and of Silke Ospelkaus in Hanover. Okay, so, okay. Okay, you probably know this kind of context. So briefly, the work is located in the context of ultracold polar molecules, composed of two different atoms, mainly alkali metals, but not only. Such molecules are produced in their absolute ground state. They have a permanent electric dipole moment, which induces anisotropic and long-range dipolar interactions, which are relevant in various contexts like quantum simulation, ultracold chemistry, precision measurement of quantum information. However, all the experimental groups who produced such molecules have faced the same problem, their limited lifetime. And this, whether the molecules are chemically stable or not. The origin of this loss mechanism is not yet clearly understood, either sticky collisions or photo-induced processes. But what is clear is that it's a two-body process. So there is a collision or a chemical reaction, and we lose two molecules at the same time. So in a pragmatic way, if we want to increase the lifetime of the molecular samples, we have to prevent the bad collision from taking place, and so prevent two molecules from getting close to each other. And this is the idea of shielding. So I guess you have already heard about it earlier this afternoon, but briefly, I will remind the principle. So I illustrate it with some long-range potential energy curves between two molecules. We assume that there is a ground curve, assumed here flat, but allowing for the reaction to take place. And there is a repulsive curve dissociating to an asymptote where one molecule is excited. And we shine an electromagnetic wave, which is blue detuned with respect to the molecular transition. So in a dressed state picture, the two curves have a crossing at the so-called condensed point, RC, and due to the coupling of the field, this crossing is avoided. And so when the molecules start a collision in the ground state, they face this engineered repulsive interaction and they go backward. This has already been observed, first of all, with static electric field with fermionic RB in the GILA group, and also with microwave fields in various groups with various molecules. The idea here is that the transition which is used for the shielding is a purely rotational transition. Now, using optical field is another interesting alternative. Actually, optical shielding was demonstrated in the 90s with cold atom. And here the considered transition was the D2 line of the alkali metals. The problem is that these upper levels have very limited, very short lifetime, and so spontaneous emission somehow deteriorated the scaling, the shielding mechanism. So if we want to apply this optical shielding with alkali molecules, we have to find a transition whose excited level has a larger lifetime. And in B alkali, it is possible. We have in particular the small B state with the quite weak transition between the capital X ground state and the small b. And actually, in 2020, we have proposed and theoretically demonstrated the possibility to realize one-photon optical shielding using this intercombination transition. However, it seems that even in this case, photon scattering is still a big drawback of this mechanism, of this proposed scheme, even if the detuning is very large and the transition is very narrow. And so another idea popped up, still using optical fields, but if we want to get rid of spontaneous emission with optical field, well, why not using two-photon transition, which allows us to generate a dark state, so which is not away from the excited state. So here we have a lambda scheme that we consider, so G1, G2, and Q. The G1 state is the initial state, so the Rho vibrational ground level. Here we ignore hyperfine structure for the moment. As an intermediate state, we take an electronically excited state. So for example, the small b state, but it could be another one. The only constraint is that the rotational quantum number is equal to 1 due to selection rules. And so due also to selection rules, the G2 state is also from the electronic ground state and lower vibrational level, but with the rotational number equals to 2. And so with those states, we can write the usual three-level Hamiltonian in the dressed picture with Rabi frequencies and detunings. We can even go further by adiabatic elimination and using an effective two-level Hamiltonian with the effective parameters given below, so effective Rabi frequency and detuning. So this is okay. This is for one molecule. But in our case, we have two molecules in collision. And so how can we transpose this scheme, extend it to two molecules in collision? Well, the first answer to that is writing an Hamiltonian, actually, the Hamiltonian of the pair of molecule. So there is the T, so the relative kinetic energy. We have the individual molecule energy, so their rotation, the dipole-dipole interaction between the two molecules, the field Hamiltonian, and the Hamiltonian describing the interaction between the two molecules and the two fields. So in order to answer the feasibility of two-photon optical shielding, we have to, well, take this Hamiltonian, basically solve coupled channel equations and extract some observables describing the scattering. But this, before doing this very hard and hard task, long task, we wanted to have a first answer on the feasibility of shielding with two photons. And to do that, we worked on the levels that we take are the potential energy curves between two molecules, like those I have shown previously to illustrate the shielding. So practically, out of this Hamiltonian, we extract some terms. First of all, the centrifugal barriers of the collision, then the individual rotations of the molecule, and then the dipole-dipole energy, which are dependent. And so we have a long-range Hamiltonian that we diagonalize at different R values. We obtain long-range curves and R-dependent eigenvectors. And so those eigenvectors are expanded on an asymptotic basis, M, on which I will come back later. And in this respect, the effective Rabi frequency can be written like this. So it's proportional to the, of course, to the eigenvectors component, but also to the matrix element of a tensor rank, of a tensor operator of rank 2 between the asymptotic basis functions. So what are those basis functions? So one possible choice would be to take lap frame and fully uncoupled bases. So we take the quantum numbers of individual molecules, so the rotational quantum numbers, and the partial wave, N and ML. In our case, we rather choose the fully coupled and symmetrized basis function. So we include with these brackets, solid brackets, the fact that we have two indistinguishable bosonic molecules, two identical bosonic molecules. We introduce as well the total angular momentum of the complex and its Z projection. And there is this plus minus sign with reflect the inversion parity of the whole complex. So in this basis, for example, the initial state for the collision that we call M1. So if we take two ground state molecules colliding in S wave, well, it's a state with only zeros and the plus parity. And in this case, we can plot the potential energy curves. And you can see on the bottom right that it is attractive and it has a van der Waals character in 1/R6. So the reaction, of course, is fully possible with this kind of interaction. So now a few words about the selection rules, which are important for our study. So first of all, the selection rules on the dipole-dipole operator. It affects both rotational quantum numbers at the same time, changing them by one unity. It can affect as well the partial wave, but all the other quantum numbers are unchanged. By contrast, for the field, Raman field interaction, it changes only one molecule at a time with a plus or minus two change. The partial wave is not modified, and the total angular momentum is modified by 0, plus minus 1, or plus minus 2 units. The other quantum numbers are unchanged. So starting from this M1, the initial scattering state, we can see that it can be coupled by this Raman interaction by only one state, which is this M2, so 0, 2, 2, 0, 2, 0 plus. But itself, by dipole-dipole interaction, it can be coupled to various asymptotic state, but for which the GI-JK couple is equal to 1, 1 or 1, 3. So now, keeping this in mind, we can go to our result for sodium-potassium molecule. First result are the lowest potential energy curves in wave number and in log scale regarding the distance. So it is between two molecules in the ground state, X, and lowest vibrational level. And you have the asymptotes as pairs of rotational quantum number. So the lowest asymptote, again, I have plotted already. It's the Gx equals 0, Gx equals 0 with the plus parity. It is fully attractive. Then we have the 0, 1 asymptote, which is used for the microwave shielding. So you have this repulsive state and the attractive state as well. But we cannot use it here because it has the minus parity symmetry. In our case, we are interested in the Gx equals 0, Gx equal 2 asymptote. And as you can see, it's good news because we have repulsive curves correlated to this asymptote. And to explain the origin of this repulsive curve, we have to remember that the dipole-dipole interaction couples the state of the kind 0, 2 with the state of the kind 1, 1 and the state of 1, 3. But the state of G equals 1, Gx equals 3 are much higher in energy, and so they are less affected by this coupling. And so the curve, repulsive curve dissociating to 1, 1, you see they go like this, and they tend to have a kind of avoided crossing, and so push upwards the curve coming from the 0, 2 asymptote. And this is what explains this repulsive character of the Gx equals 0, Gx equals 2 curves. Actually, so this is a second order effect of the dipole-dipole interaction, and so it scales as it's a van der Waals stuff, so it scales as r to the power of -6. We can confirm this. So on this figure. So now still it's a zoom on the 0-2 curves with energies now in megahertz. So widely used for the shielding community. And so we can see actually that we have 3 repulsive curves, so A prime and B prime, but also C prime. It's a very small barrier, but still a barrier. We can make a fit, for example, of A prime and C prime, and it confirms that we have both the centrifugal barrier and the repulsive C6 terms. So this really is the origin of this repulsion. And if we take the A prime, we can identify the crossing, because on this figure, we also report the lowest curves shifted in order to have a detuning of 70 megahertz. And so we see a crossing here at this codon point of 240 atomic units. So this choice of 70 megahertz actually comes from this paper of Gulven and Luca, where so there is a similar detuning, and it's a microwave shielding, and we have also crossing, so between now the repulsive curve coming from the 0-1 asymptote and the asymptotic, the lowest curve was shifted, and so you have this crossing here at 340 atomic units, so further apart, but the same kind of crossing. So we can see some similarities, let's say some mapping in some extent between the two mechanisms. But now, we see that we have a repulsive curve, and they can cross with the lowest one, but in which extent those curves can be coupled? Well, to answer this, we had a look at the eigenvectors, at the R-dependent eigenvectors of our curves. So, and we monitor, you remember, the asymptotic state M1 and M2. So M1 is the one correlated to the initial scattering state. And so we can see that the lowest potential energy curve at different condon points has a very, very strong character of this M1 asymptotic state. So it doesn't change a lot. The situation is different for this M2, so we have the A prime, B prime, and C prime as candidates for the G2, so the final Raman state. And you can see that the majority of M1 at 240 is still within the C prime state, so the very small barrier of potential. But there is still some components, sizable components in A prime and B prime. And so this opens the possibility to make coupling by two-photon between the initial potential curve and these repulsive curves as well. Now, if we decrease a little bit the condon point, so the intermolecular distance, we have more mixing among the A prime, B prime, and C prime. So this is because as energy, or the distance decreases, the different curve lose progressively their asymptotic character, because there is more and more mixing due to the dipole-dipole interaction. So now that we have the possibility to do the coupling between the two curves, now we can look at if we want to target some effective parameters, like detuning and Rabi frequency, like the one used in this experimental paper on CEF for the microwave. The question is now, what physical parameters, so physical Rabi frequencies for the two fields and detuning must we achieve? And in the end, which kind of laser intensity? So here you see, as function of the detuning capital delta with respect to the excited curves, you can see the Rabi frequencies, and on the right axis, the laser intensity. So laser intensity takes into account the fact that we have the transition dipole moment between the capital X and small b state. And so you can see in this case that, okay, Rabi frequencies to achieve those effective parameters are rather large, and the intensities as well. We can actually, by taking smaller effective parameter, reduce the Rabi frequencies and the laser intensities to more moderate values. If there is also a possibility to still decrease the necessary laser intensity by taking transitions which are not to the small b state, but rather to, for example, the capital A, for which the transition dipole moment will be larger. Okay. So now I would like to say a few words as well about the potential energy curves for one molecule in the ground state and one molecule in the electronically excited state. So this will be the state, intermediate state for our Raman scheme. So we are especially interested in those states because, okay, the Raman transition takes us to this Gx equals 0, Gb equal 1 with minus parity. You see that it is almost degenerate at this scale to the Gx equal 1, Gb equals 0 asymptote, because the rotational constant of the two states are very, very, very similar. And so we can see some curves here, which are also the resonant dipole character. So in one of the R3, we have the repulsive curves that we have proposed for our one-photon scheme. And we have also attractive curve here, the ones I and K, which are also significantly coupled with the ground state, and which we can retain. And we have a negative red detuning because the different constraints on our effective model impose you that we have a negative value of capital delta. Okay, so now I come to my conclusion. So we have opened the door to the realization of two-photon optical shielding, in particular with the case of NAK molecule. We have shown that there are correlated to this accessible asymptotes some repulsive potential energy curve, which can be coupled by two-photon transitions with the initial attractive potential energy curve. And so we think that this two-photon scheme will help us to get rid of spontaneous emission and photon scattering. So we have seen that there is some kind of correspondence or mapping with the one-photon transition, at least regarding the characteristic of the curves and the crossings. We have shown this for the small b state, but it's also possible to use other intermediate state like capital A or capital B. Now, the next step, which is in progress actually, is doing the full scattering calculations. And in this respect, so you can, first of all, have a look if you want more details at this publication, which has recently come out. But of course, also visit Charbel Karam's poster, who is here in the audience, and who is also doing the scattering calculation. So yes, please go and visit him to have more details, and yes, if you want to discuss more and in person about this subject. Finally, I thank the founding agencies and administrations, and I thank you for your attention.
Can you hear us? Can you hear us now?
Yes, I can.
Have we got questions in the audience?
Thank you for the interesting talk. I have a question. So you mentioned the mapping to one-photon case, and then there's a two-photon detuning. How close to the two-photon resonance you can go to have an idea before you're killed by spontaneous emission? Because because you're going to get problems from spontaneous emission if your two-photon detuning is small, right?
The idea is that if we take the small delta, so the two-photon detuning equals to 0, we are able to generate a dark state, which is which has no component of the electronic excited state, and so we in this case we can make sure to get rid of this spontaneous emission problem, because effectively the molecules will not populate this electronically excited state.
Right, but this is kind of like, did you analyze the noise on the lasers, the noise due to, like, you're never going to get the perfect, dark state in this case, right? Because there's imperfections in experiment.
Well, I think, we haven't analyzed in details the noise of the null, but what we have determined with our experimental colleagues from Hanover is that because we have beams with very similar transition with very similar wavelengths, because they addressed very close rotational levels, and so they have very similar wavelengths. They could be both beams actually could be generated from the same laser, and then with with an electro-optic or acousto-optic modulator. So in this respect, the noise should be rather small compared to the situation where it would come from two different lasers. This is what I can tell for the moment. We haven't analyzed in more details this noise influence, but yes, this is for the moment what we can say.
Okay. I think, shall we thank Maxence again for his talk?